Yesterday we defined energy as the ability to do work, and we decided that we had two types of energy that we could categorize every bit of energy into. What were those two categories? Potential and kinetic, right? Potential and kinetic. Kinetic energy was differentiated from potential energy, and the kinetic energy is actually doing work right now, right? It's the energy of motion. When something's moving, it has kinetic energy. Whether we're talking about a molecule that's moving around or we're talking about a planet that's moving around, they both have the same kind of energy, kinetic energy, because it's based on motion. The second kind of energy we said was potential energy. And potential energy isn't energy that's doing something right now. Rather, potential energy is the energy that has the potential to do something down the road. In other words, it's stored energy. Can you give me an example of potential energy? One kind of potential energy that we'll deal with. One kind of potential energy, in fact, that we have already dealt with, that your homework questions were on. Gravitational potential energy, right? We're going to talk about another type of potential energy on Monday. We briefly mentioned a whole bunch of different types of potential energy yesterday. Again, we'll do one other type in quite a bit of detail on Monday. There's two equations that we've learned so far for energy. The first one was for kinetic energy. EK is equal to, right, 1/2 mv squared. What did m stand for? Mass. And what are the units for mass? Kilograms. Okay, as opposed to chemistry where you usually use grams for mass, right? We're going to use kilograms here. What about V? What does V stand for? James? Speed. Yeah, not velocity. It's speed. So the direction is not important. That's going to be measured in meters per second. Gravitational potential energy, we're going to say EP is equal to mgh. M stands for mass in kilograms. G is 9.81 meters per second squared. And H stands for what? The height, relative to something. Okay, relative to the ground, relative to my hand, relative to something. Okay, we got to be consistent here, and that's the only thing we need to remember. If we're measuring the potential energy relative to the ground, then use the height relative to the ground. If you're measuring the potential energy relative to the top of a table, then use the height relative to the top of the table. What units would kinetic energy be in? Ryan, what units are kinetic energy measured in? Right. And what units are potential energy measured in? Jeff? Joules. Good. They're both measured in joules. Is kinetic energy a vector or a scalar? Vector or scalar, Quinn? Is kinetic energy a vector or a scalar? Good. Is potential energy a vector or a scalar, Braden? Potential energy is a, no, it's a scalar. Energy is always a scalar. There's no direction ever associated with energy. Does that make sense? Okay, we can have a negative change in energy, but that doesn't mean the energy was to the left. It means we lost energy. Okay, has nothing to do with direction, just has to do with whether we gained or lost. Does that make sense? All right, combined, we mentioned this term briefly yesterday. Combined, these two types of energy are referred to as what? Starts two words. First one starts with an M. Mechanical energy, right? Mechanical energy is the sum of kinetic and potential energy. All of those energies added together. All right, you had three questions for homework last night on page 298. Any issues with any of those three questions, please? None? Number 3, okay. Any others? All right, number 3 is the one that I would have assumed would give people a little bit of a challenge. Okay, it's phrased a little bit differently. We got to do something beyond just multiplying m times g times h. So let's do that one now. It says a winch pulls a 250 kilogram block up a 20 meter long inclined plane. So a hill that looks like this. Here's the block, 250 kilograms. Okay, the distance that it's pulled is 20.0 meters along that incline. And we've got an angle here of 35.0 degrees. If I want to find the change in potential energy, then we've got to find the final potential energy, the initial potential energy, and then subtract them. Let's assume the initial potential energy is, what's the easiest thing to do here? The initial potential energy at the bottom is 0. So we're assuming this is our zero height, right? Therefore, our potential energy is zero. We could have defined this as our zero height or this is our zero height, but it wouldn't have made any sense to do that, right? Usually it's pretty clear what makes the most sense to define as your zero height and therefore zero potential energy. Okay, in this case, it's very clear. All right. So the change in potential energy is equal to the final potential energy minus the initial potential energy. But the initial potential energy, since we define the bottom as zero height, is zero. In other words, the change in potential energy is simply equal to the final potential energy, mg times hf. But we don't know the height. Right? It's not 20 meters. It's not 250 kilograms times 9.81 times 20. So what is it? How do you get that height? How do you get this height right here, which is really what we want, right? Not the Pythagorean theorem, but whoever said that, you're close. Who said that? You're close. It's not the Pythagorean theorem. A little bit of trigonometry, right? Okay, we've got the angle, we've got the hypotenuse. We're looking for the opposite side. Let's say sine 35 degrees is equal to opposite over hypotenuse. H is equal to what there? 11 point, let's go 3 or 4 decimal places. 471. Okay, thank you. 11.5471 meters. So let's plug that in now as our final height, 11.5471 meters. And we get our change in potential energy. I assume that works out to be 2.81 times 10 to the 4. Yep. 11 point. Okay, so 11.471. Yeah. Okay, thank you. Uh, 2.81 times 10 to the 5, 10 to the 4 joules is our answer there. So I know I had this question from a couple people yesterday. You know, essentially it boiled down to this, but we're not going up that height. Like we're not going straight up. Okay, we're going at this angle 35 degrees at 20 meters. So how can my potential energy be the same going up this path right here as if I was just going straight up here with a height of 11.47 meters? It doesn't matter how you get there. Okay, if you get to the top right here, you have the same potential to fall, okay, to the bottom if you went up this way or if you went up this way. Okay, if I take this block away, this whole hill away, I will fall at the same rate okay, whether I went up this hill this way or whether I went up this cliff this way. Make sense? Doesn't matter how I got that. Any more questions? All right.